First thing I want to do is thank you all for the opportunity to present probably the biggest, most challenging research project in my career, and I just appreciate the opportunity to come and talk about it. The presentation I'm going to tell you today is just a small part of a big national project that we're working on. It's an NCHRP project. It's about the effects of recycling agents on asphalt mixtures with high RAS and RAP binder ratios. And you can see there's a lot of people working on this project, and I just try to, herd the cats a little bit. It's a great team. Some members are in the audience, and I appreciate everybody's input. So, as we all know, the motivation of increasing the recycled binder ratio, or the RBR, is both economic, because we don't have to use as much virgin materials, environmental, because we're recycling materials, and some engineering benefits. But when we get those RBRs up too high, we have some issues, such as the material is too brittle. It's too brittle. It's too stiff and too brittle. We also don't really know what happens with these mixtures with respect to aging. There's also a big challenge in terms of the blending. What is the actual blending that's occurring between the virgin binder, the recycled binder from the RAP and the RAS, and if we add in any recycling agents? And then finally, the mixture performance, especially with respect to cracking. That's what we're worried about, because we have these stiff, brittle mixes with high RBRs. So the idea is, let's try to use higher RAP and RAS contents, but use a recycling agent to sort of mitigate those stiffening and embrittlement effects. This is not the greatest picture since sliced bread, but it's okay. It's our latest field project that we just worked with Wisconsin. So currently in Wisconsin, they're allowing a 0.22 RBR with all RAP. And they have put down a mix with this, what we call the DOT control mix. And then we're trying to see, can we go up to 0.31 RBR by using a recycling agent? And when we do that, of course, our RAP aggregate goes from 26 to 34%. Our virgin binder goes down from 4.3 to 3.7%. And so the idea is, can we get those benefits that we want by using recycling agents to mitigate the effects of the stiffening and the embrittlement? And do those recycling agent effects last with aging? That's a big thing. So maybe they work initially, but do they last with aging? So just to give a little sense of where we are in this project, we're currently in phase 2. Phase 1 was a literature review and a survey of DOTs. Phase 2 is kind of where we are right now. We're trying to, it's a big lab experiment basically, but all of our lab materials are tied to field projects. And then in phase 3, we're going to try to apply some of the tools that we've come up with to lots of different material combinations in the different field projects. And I'll speak about that at the end. So some of the tests that we're utilizing in phase 2, we're doing quite a bit of binder testing. Then we're doing a little bit of mortar testing, and mortar testing is a way to not have to extract and recover the binder out of the RAP and the RAS, so you're getting a more realistic blend of materials. And for both of the binder and the mortar testing, we're doing the PG grading using the DSR and the BBR like we normally would. And we're using a parameter that's gained a lot of attention recently called delta TC. And all that is the temperature where the stiffness criteria in the BBR is met, minus the temperature where the M value threshold is met. And it's a good indication of embrittlement. Like basically you want to use base binders with recycled materials that are S controlled. So you want to have a positive delta TC, but lots of binders that we use are M controlled. So their delta TCs would be negative values. We're also using another parameter quite frequently that's kind of gained some recent attention called the Glover-Rowe parameter. And the Glover-Rowe parameter is just a different combination of G star and phase angle. So it's just, instead of G star over sine delta or G star times sine delta, it's just G star times the cosine of delta squared divided by sine delta. Okay, so it's just a different combination of G star and delta that you would get out of the DSR. However, it's an intermediate temperature property. It's at 15 C, and it's at a set frequency of 0.005 radians per second. And then we came up with sort of an initial idea of, and I'll show you on a plot, but to look at what we call rejuvenating effectiveness. So we sort of had an initial rejuvenating effectiveness as this Glover row parameter for that DOT control mix minus the Glover row parameter for the recycled mix that was shown on the right of the previous slide, divided by the DOT control one, and all those are log values. So just how much do you improve over the DOT control? And we would track that with aging, and you're going to see how aging definitely affects it. And then, of course, we're also, in addition to rheology parameters, we're also looking at chemical parameters, such as oxidation measured according to carbonyl growth by FTIR. We're also doing mixture tests. So we're doing binder, mortar, and mixture tests. And for mixture, we're looking at stiffness in terms of resilient modulus at 25C, because it's easy and cheap and repeatable. And on the same specimens that we do resilient modulus, we're able to run the semicircular bend test and get something called the flexibility index. So we're able to get an intermediate temperature cracking resistance of the mixture. We're also doing fatigue life by the simplified viscoelastic continuum damage test, and we're also doing the resistance index by the UTSST test. All that is a better, improved TSRST test, which was the thermal stress restrained specimen test. It just has a few extra, it has more analysis, and it measures the strain in the specimen that's not restrained also, an unrestrained specimen. So it's just an improved thermal cracking resistance test. So we have 2 cracking resistance tests at intermediate temperatures and 1 at low temperatures. So the initial phase 2, before we went to the panel meeting, we looked at a field project constructed in Texas in 2014, where we were lucky that as this project was starting, there was a Texas project that was being utilized on a TxDOT research project, and it used a 64-22. The target binder was a 70-22, but when they add in RAP and RAS, a lot of times, right, by the TxDOT specifications, you do a substitute binder and you lower the high temperature grade. So we have a PG 64-22. We have 0.1 RAP binder ratio and 0.18 RAS binder ratio, and it was manufactured waste type of asphalt shingles. That's important to note. And really, we shouldn't combine this and say, oh yeah, it's 0.3 RBR. It's really important how much of that is RAP and how much of it is RAS. So we always show both now. We also added in a tall oil, which is kind of the new greener types of recycling agents. In addition to that, we wanted to expand that for our big laboratory study. And so we wanted to look at, okay, higher RBRs. We were charged with looking at 0.3 to 0.5 in this project. So we looked at 0.4 RBR with only RAP, and then we decided to look at 0.5 RBR, where we had 0.25 from RAP and 0.25 from RAS. We also looked at tear-off asphalt shingles, as those are more prevalent and much more aged than the manufactured and waste shingles. We also wanted to look at a second recycling agent. So we looked at one of the older, more traditional types of recycling agents, an aromatic extract that we call A1. And then we also looked at 2 different binders, a very high quality binder from New Hampshire, which is unmodified, but it's a 64-28, and you're going to see it has a very good positive delta TC value as compared to the PG 64-22 delta TC value. And we also wanted to look at a polymer modified binder. So we looked at a Nevada binder that was used in another field project associated with 9-58. And I mentioned we're looking at TOAS too, tear-off asphalt shingles. Okay, so I don't have time today to talk to you about everything that we're doing in this project, but one thing I think that might be of interest is that it's sort of like to start the whole project, we have to figure out, quote unquote, an optimum recycling agent dosage that we want to use in the mixtures, because we cannot for sure test all those mixture properties on multiple recycling agent dosages. So we've been working with the binders, which of course assumes complete blending, which isn't exactly the realistic scenario in the mixtures, but I'll speak a little bit about that toward the end here. So we came up with a preliminary recycling agent dosage selection method, this trial number 1. The first approach we came up with in phase 2, and then in phase 2B, which I'm going to describe in just a minute, with some more materials, we came up with these second 2 approaches, and we think we finally nailed it down. So I think this is hopefully of interest. So the first one, actually all 3 of them have these steps: select the materials, prep the materials, conduct the laboratory tests, and then those 3 different approaches they differ in how we actually select the dosage. So all of them have this step, selecting the materials, selecting the target grade, which sometimes can have a bump up due to traffic, and then the base binder grade that might have a bump down due to the use of recycled materials, a substitute binder. Select your RAP and your RAS sources, and we're definitely finding that Texas RAP is way different than New Hampshire RAP, right, in terms of the aging of the materials. Pick your recycling agent. There's lots of different types. Right now I think we've looked at 6 different types. I mean, large categories of types, not just different brands. And then you got to pick what's your RAP binder ratio and your RAS binder ratio. This is the hard part, extracting and recovering the RAP and the RAS binders. Nobody wants to do that, including my undergrad students. But it's pretty necessary. We're looking into some of the equipment that's coming online that could make it safer and faster and easier. We don't know. We're going to try it out maybe. But you got to get that binder out so that you can add it to the virgin binder and the recycling agents. So we usually do 3. With no recycling agent, that would be 0% dosage or the control. With a low recycling agent dosage, maybe around 2%. That's kind of in terms of how the manufacturers of the recycling agents, how they recommend what you do. 2% or less, you basically just add it in there. Okay, you just add it in there. 2 to maybe 5%, you basically take out some virgin binder and replace it with recycling agent. And so there's this addition versus replacement in terms of how you add the recycling agent. So we look at 2% because we thought that was a pretty low dosage, and then we look at 10% because we thought that was pretty high. Well, we thought that was pretty high until we started looking at the material combinations that we used. But even, we do have to extrapolate a little beyond 10%, but we still feel pretty good about it. Okay, then you got to grade it. So you get the PG high temperature grade or PGH and the PG low temperature grade just by AASHTO M320, just like we always do. We do that for the target binder. We do that for the control binder with no recycling agent, and then for the 2 ones with a low and high dosage. Okay, and then when you plot these, we basically plot the PG high, the high temperature PG grade versus the dosage. We're going to have 3 points, 0%, 2%, and 10%. The green line is the original G-star over sine delta. What was its PG high temperature grade at the threshold? And then the purple is the rolling thin film, because you gotta figure out what both of those are and what's the limiting one. And then on the right side, we're gonna graph 2 more lines, and we're gonna put the low temperature grade. And here we have the M controlled is in blue and the S controlled is in gray. And what you see here is the distance between these 2 lines is actually the delta TC value. And as we keep adding recycling agent, the distance between those 2 lines is going together, which is good. So the way that the first trial of restoring the PG low temperature grade, so what we do is we come along here. So this is controlled by M control, right? The M value is saying it's a minus 15. And the S value is saying it's a minus 26. So it's an M controlled when we're over here at 0% dosage. So we keep adding in dosage along a linear relationship, and everything that we've tested seems to be linear. So we're using a linear relationship. We feel fine about that. I don't know what would happen if you added 25%, but you're not going to add 25%, so it's okay. So at these dosage levels. So we add it in until we get to a minus 22, okay? Because we started off at a minus 15 or so. We got to add in recycling agent until we get to a minus 22, because our target is 70 minus 22. That's what we're trying to get to. That would be like if we just had virgin binder. That's what we're trying to get to. So when we get to minus 22, we have a dosage of 4.5%. That sounds reasonable. And we look at what our delta TC value is, minus 10. And then at the next step is that, so we restore the PG low temperature grade to minus 22, and then we come up here and we just check what is the high temperature grade at that point. So the high temperature grade at the same dosage of 4.5% is 73. So we're a 73 minus 22, which hits the target of 70 minus 22, and we're done. Okay, so this is for a particular blend, of course, with a particular mix of RAP and manufactured waste shingles, with a particular base binder and a particular recycling agent. So that's what we just went through in that example, what I just said. So you're of course using the warmer low temperature grade, which was M controlled, and then you're verifying it using the colder high temperature grade, which was the original binder, not the rolling thin film. Okay, so that's the first approach that we tried. And we note the PG, or note the delta TC. Now, what if we try it at one of those high RBRs, 0.5 RBR with a really high RAS content, 0.25 RAS content. Okay, so we get all 4 of our lines. You see the crazy M value line, right? But you do see that it's closing in to the S value line. The delta TC is getting smaller. So the first thing we do is we come along this very steep blue line and we restore to a minus 22. So once we get to a minus 22, that's at a dosage of 10%, okay, and a delta TC of minus 11, which seems high. And then we're going to check the high temperature grade, and the high temperature grade at that point is a 78. That's not a 70 minus 22, right? That's a 76. So we would do a second step where we'd continue down this line, adding in recycling agent until we bring it down such that it's a 70. So we need to get this number in half, I forgot to mention that, in 0.5% increments. So as a practicality measure, we're doing this in 0.5% increments. So we add it in until we at least get below a 76. So in this case, we get a 74. And then we just double check. We're at a minus 25, which is still a minus 22 grade. So we get a 74 minus 25 with our new dosage of 11.5%. That meets the target, and it also reduces the delta TC to minus 10. Now, what is the value of this delta TC thing? So the delta TC has been shown to be tied to some age-related cracking at airports, and some people have suggested a value of minus 5 is sort of, you don't want to get more negative than minus 5 after 40 hours of PAV aging. Of course, this is after 20 hours of PAV aging. So 40 hours of PAV aging, it's like, forget that. That's just way too high in terms of a dosage. And we also don't know really if that minus 5 is the right threshold or not. So for right now, we're just kind of keeping track of those delta TC values. Okay, so if you look at trial approach 1, this is a bunch of data, including the one I just showed you. So I just showed you this 11.5, and I just showed you this 4.5, right, with a delta TC of minus 10. I think I showed you that one. It says a delta TC of minus 9, but anyway. Okay, so what you see here is the blue values are the Texas 64 minus 22 base binder that's used in the field project, the T1. You see the delta TC of that base binder is pretty negative. It's negative 4.6. Remember, we want it to be positive. The New Hampshire binder is in green. It has a much better, it starts out from a better place. It has a much better delta TC to start with, so it has room for those recycled materials. Then we have the red is the Nevada 64 minus 28 polymer modified binder. And from this line over to the left, this is all with Texas recycled materials. These two little short guys over here are with Nevada wrap only. So no RAS and much less aged wrap. So what you see here is, number one, it's a little bit better quality in terms of the base binder, but what you see is that the recycled materials are just not nearly as stiff, okay? They're just not nearly as stiff. This is also mixing and matching. This is a 0.3 wrap only. Of course, this is a 0.3, but with RAS added in there. This is a 0.4 wrap only. This is that 0.5 high mixed. This is a 0.4 wrap only. So it's kind of a mix. You don't need to look at all the detail here, but suffice to say that we definitely can see the difference in, and this is an aromatic extract. This is A1. I'm sorry, it's not labeled. But you can see that for A1, in both of these cases, A1 needs a little bit higher dosage. But who cares? That's just a matter of how the materials are acting together. But the A1s needs a little bit higher dosage. We definitely see a difference. This is the manufactured waste shingles. This is the tear-off shingles, everything else being the same. So you can see that a higher dosage is needed with tear-off shingles. You can also see the effects of these different base binders. And this final one over here is, it's not labeled, but it's kind of. It's in Indiana binder, Indiana recycled materials, and a recycling agent that we used in the Indiana field project. So it's just another data point. But all of these are by that first trial approach. Okay, so that's what we think. We thought that was the optimum recycling agent dosage. So we also wanted to look at how does the rejuvenating effectiveness change with aging. So this is that DOT control binder, and this is the black space parameter. So this is log of G star at that 15C and 005 radians per second versus phase angle at 15C and 005 radians per second. So this is showing stiffening or softening, and this is showing flexibility or embrittlement. Okay, so it's capturing both rheological parameters on a single plot. What you see here is rolling thin film oven of the DOT control binder. Then you see PAV 20 hours and PAV 40 hours. So a single binder marches across this diagram from the lower right corner to the upper left corner. Oh my gosh, I don't have any time. Okay, so I'm going to have to go faster. So you'll see that, look what happens. When we put the recycling agents in there, oh, that's great. It goes back down and toward the right. So that's good. And that's what we want. But what happens with aging is that it's still out here past these cracking thresholds. And these are very loosely based on those airport pavements, but still there's some kind of threshold. So it's not good with aging. Okay, we're going to have to skip. And that's basically what these are showing. The binder rejuvenating effectiveness is lost with aging. We did some mixture validation with both the cracking at intermediate temperatures and stiffness at intermediate temperatures. And then we went to a phase 2B where we added in 2 additional recycling agents. We also added a better base binder from Indiana and a softer base binder. So we're just adding in more combinations. And we said, you know what? We better check the rutting resistance once we get to that lower right-hand corner of the black space diagram. So we're doing some of this. I can't go into the detail of that today, but we are doing that. So the second trial approach was, now let's try to restore the delta CC to that -5 threshold number. And when we do that, you see that that's the top of these. It goes from 4.5 to 12.5. So the example I showed you, you got to really increase the dosage. And so when you do that, the Indiana blends, this is the better base binder with a delta TC of -1.2. The better base binder, it's already at -5 for delta TC. You see how there's no additional stacked element here. So the Indiana would have the same number whether we did it by trial approach 1 or trial approach 2. But what we saw, and we changed the parameters for this black space to 21C, which is more applicable for a 64 - 22. So everything is kind of shifted already. The Indianas, it doesn't make a difference. At those low recycling agent dosages, it doesn't make a difference. With the Texas, though, we do see that this is the initial values at 21C, so everything just kind of moves down and to the right. But when we up those dosages to 12.5, oh my goodness, we're way down here, and we're probably over softening. So we check that. Yes, Hamburg rutting. Okay, so we can't do that. So we got to balance that. So we did, I'm not going to go through this in detail, but we did a third trial approach where now we're going to, it's kind of like in mixed design. We're going to put as much binder in there for durability and cracking resistance, but not have a rutting problem. So that's kind of what we're thinking. And so we're going to restore the high temperature grade. When we restore the high temperature grade, we get a dosage that's between that 4.5 and 12.5, right? So that's kind of where we want to be. And when we do that, it looks like this in black space. It's not nearly as over-softened as it was before. And we did check it in Hamburg. In Hamburg, we really couldn't separate out moisture and rutting effects, so we did a dry Hamburg, and in dry Hamburg, it passes. So we think this might be the right approach, this restore the PG high temperature grade. We're also looking at a few other parameters in black space, so how things age in this direction and how they get rejuvenated in this direction. And that's what we're trying to do. We're trying to finalize this and match the binder and the mixture, and then go ahead and characterize the mixtures at this selected optimum and look at cracking resistance and embrittlement. This is my last slide. And so we also have different combinations of materials for phase 3, different combinations in Nevada, Wisconsin, Indiana, hopefully Delaware, and Texas. So this is a pretty big effort, and I hope that I at least hit the high points. I'm sorry I had a little too much to say.